3.4 Laplace transform of Dirac delta function. Before we go to the Laplace, okay, let us see the definition of Dirac delta function. Okay, so the Dirac delta function is actually a function that model the tall and narrow spike function. Okay, so mathematically it is defined here. Okay, so the notation is del. Okay, so this is delta. Delta t minus a is equal to infinite. Okay, infinite number, infinity. If t equals a and anywhere else, it is 0. Okay, so in terms of diagram, we can draw like this. So this is your x-axis. Okay, so somewhere here is t equals a. Okay, so at this point, okay, the value of the function is infinite. Okay, so basically on the paper you cannot really draw. Okay, because at this point, okay, the value is infinite. So basically it is endless line. Okay, but for the purpose of illustration, let us stop here. Okay, so you can see in this diagram, okay, a very large force acting in an extremely short interval of time. Okay, only at t equals a, the value is infinity. Okay, anywhere else, it is 0. Okay, so in other subject or in other application, we know this as impulse. Okay, in physics, okay, in physics application, we know this as impulse. All right, so in terms of the application, or if we can think of something that is close to us, okay, so you can imagine, okay, when you hit a nail with a hammer. Okay, so the blow of the hammer, okay, so the blow of the hammer is actually an impulsive part of a force, which can be modeled as Dirac delta function. Or in other scenario, okay, when you hit a snooker ball, okay, with a stick, okay, so the impact force is actually a Dirac delta function. Okay, so those are the things that you can imagine, okay, for the Dirac delta function. Okay, now we want to go to the Laplace transform. We want to know the Laplace transform of Dirac delta function. So this is actually the concern, our concern in this subtopic, to know the Laplace transform of Dirac delta function. Okay, so in your table of Laplace, you have these two. Okay, only the last two here. If we can refer to the table of Laplace, okay, this is what you have that are related to the Dirac delta function. Okay, so the Dirac delta function t minus a, okay, so the transform is exponent, okay, negative as, and if you have Dirac delta function and then multiply to some function in terms of t, then the answer would be in the form of exponent negative as times the fa. Okay, so basically if you know your ft here, you just substitute t equals a, then you get the answer. Okay, so this is very I would say straightforward calculation in terms of Laplace. Okay, okay, so now let's see example 14 to illustrate this. Find the Laplace to the ft if ft is given by exponent negative 2t plus Dirac delta function t minus 2. Okay, so what we want to have here is the Laplace to the, so it means we can separate into two Laplace, okay, by the linearity property. So it is Laplace to the exponent negative 2t plus Laplace to the delta t minus 2. Okay, so for the first part, okay, based on the table, so we know that this is 1 over s minus a. Our a is negative 2 here, so we have s plus 2. Okay, so look for the Dirac delta function here. So delta t minus 2 here can be mapped to, so this one can be mapped to, okay, what we have in a previous page. So this one, okay. So the Laplace of Dirac delta t minus a is just exponent negative as. So you should know, you should identify your a first. Okay, so this is mapped to, okay, Laplace of delta t minus a, which is exponent negative as. That's it. Okay, so the answer would be, so in this case our a is 2. Okay, so it is just exponent negative 2s. All right. Okay, very easy. You just refer to the table. Okay, and then for example 15. Okay, for example 15, find the Laplace transform to the t cube times the Dirac delta function. Okay, so this one now need to be mapped to the second function that we have that are related to the Dirac delta function in our table. So it is mapped to Laplace of ft times Dirac delta t minus a, which is exponent negative as fa. Okay, so by mapping to the table, then we know that in this case our a is pi over 2, t minus a. Okay, so a is pi over 2. Then our ft is, okay, so ft is the function, okay, that you multiply to your delta function. Okay, so what we have is t cubed. Okay, so the answer should be exponent negative as times fa. So since we know our ft is t cubed, therefore fa is just f pi over 2. Okay, so you just substitute pi over 2 power of 3 because ft is t cubed, so f pi over 2 is just pi over 2 cubed. So the answer then would be the Laplace to the t cubed delta t minus pi over 2 is just exponent negative as, so pi over 2s, don't forget the s, times the fa, so fa is pi cube over 8. So that's it. Okay, very simple for the Dirac delta function. Okay, for example 16, we have Laplace transform to the sine 2t delta t minus 2. Okay, so again this one can be mapped to, okay, similar to example 15, okay, mapped to the Laplace to the ft delta t minus a, which is exponent negative as f a. Okay, so in this case, we can see that our a is 2 and then ft is sine 2t. Okay, sine 2t. So what we want to have is fa. So our fa is f2, which is sine 2 times 2, which is sine 4. Or equivalent to, okay, decimal number according to your calculator. So therefore, the Laplace to the sine 2t delta t minus 2 is then equal to exponent negative 2s fa, which is sine 4. Okay, so that's it. Okay, very straightforward calculation. But normally in the test or in the exam, okay, the Dirac delta function will be put together in the initial value problem. Okay, will be asked, okay, in the form of initial value problem or boundary value problem or in the system of differential equation, okay, which is the last part of this chapter. Okay, very unlikely to be asked in this direct form, okay, as you have in the 3 examples that we have discussed earlier. Okay, but in terms of calculation, it is very straightforward, very simple. You don't really need to find the Laplace to the ft. Okay, in a previous discussion, normally when we get the ft, we need to find the Laplace to the ft, but not for the Dirac delta function. Once you know your ft, you just want to have fa. Okay, so you just basically substitute, okay, t equals to a, okay, whatever value of your a. Okay, so that's for the Dirac delta function. So it means we are now finished on the first part of this chapter, which is finding the Laplace transform given the function ft. Okay, so in the next topic, in the next subtopic, we will start discussing on the inverse Laplace. Okay, where you were given the function in terms of fs, you want to know what is the function in terms of t. So you were given the transform, you want to know what is the original term in terms of ft. All right, so that's all for now.